So good evening. Can you hear me in New York? You can just wave if you can hear. Thank you. I haven't been able to find my favorite Sharpie marker, so I'm experimenting with pens this evening. So there's one pen. Here's another pen. Let me ask how that's working. Can you see this okay?
Yes.
Okay.
Yes.
All right. And this looks actually a little better to me. Maybe I'll use that. Let me close the door here before we get started. Okay. So my plan tonight is to talk a little bit about futures and then about change of measure and change of numeraire units in which we keep account. And then next week I'll be there in New York conducting office hours in the afternoon before the review session and class in the evening. I put an announcement about what will happen next week up on Blackboard, so I'll let you read it there. Are there any questions before we get underway this evening that I should know about before I launch into the new material? Last week we were talking about the Ho-Lee model. In fact, we've been talking about that for some time. Ho-Lee. So the short rate, the instantaneous interest rate, has a differential that is A du plus sigma dw tilde of u. And if I integrate that from, say, little t capital T, then R of capital T is R of little t plus A of capital T minus little t plus sigma of W tilde of capital T minus W tilde of little t. And as always here, the little t comes before the capital T. And we talked about a contract that pays the interest rate at capital T. So we let S of little t be the price at time little t of a contract paying R of capital T at capital T. And I made the comment that nobody buys a contract that pays the interest rate. You buy a contract that pays the interest rate applied to some notional amount over some interval of time. But the notional amount times the interval of time just factors out of all the equations. So I'm just taking that to be 1, so I don't have to keep writing them. And last week, we computed the price of S. So last week, T, and we discovered it was equal to some function of T and R of T. You can either argue that using the Markov property, or you can just compute it, which is what we did last week. And if you just compute it, then you can see what that function is. That function satisfies a partial differential equation. The martingale here is discounted S. D of t, S of t is a martingale. And if you use that fact and the 4-step procedure, you'll find the partial differential equation that this function satisfies. And that equation is minus R times G plus the time derivative plus A of G sub R of T and R plus 1/2 sigma squared G sub RR of T and R is 0. I think on Saturday, I haven't looked at the recitation transcript, but on Saturday Ted was planning to actually take this function G that we computed last week and check that it satisfies the partial differential equation. Does anybody know if that happened? Does anybody remember doing that? Do you remember checking last week that D of T, S of T is a martingale on Saturday? Does anybody know what happened at recitation on Saturday? Not hearing any objection, I'm going to make the statement that in recitation on Saturday, Ted showed you that D of t, S of t was a martingale, and he showed you that this function g satisfies this partial differential equation. Does anyone want to argue with me? If not, that statement will stand and we'll move on. Okay, so I'm going to move on. We have a review session coming up.
Hey, Professor.
Yes.
It seems like a lot of people, at least from New York, we haven't seen the recitation. So if it's something really important, you know.
There's an exam coming up, and you'll want to be able to do these calculations. So it's not that you need to know this particular calculation, but if you need practice doing these calculations, then you want to, that's an opportunity to see an example. If you take the S of t, we did compute S of t last week. If you're confident that you could do both of these calculations, then of course you don't need to see an example. I'm going to do something different today because I don't want to repeat that. I want to talk about hedging with futures. So it's often the case that futures contracts are more liquid than the underlying on which the futures are written. And so if you have some kind of derivative security, you often want to use the futures contracts as the hedging instrument rather than the underlying itself. And in this particular case, I'd like to actually just do the calculations and see how that goes. So the futures contract, we're going to do the futures on S, the price at time little t for delivery at capital T of a unit of S. Now, these two processes, S and R, are different processes. Let me put it back here so my picture's not in the way. So S of t and R of t for little t's between 0 and capital T are different processes. One is an interest rate, and one is the price of a contract that pays R of capital T at time capital T, right? And the price of a contract that pays R of capital T at time capital T, the price of that at little t is not R of little t. You have to compute it out and figure out what S of t is. These are different processes, but at the final date, the value of the contract that pays R of capital T is R of capital T. So they do agree at the final time, even though they don't agree at earlier times. So when I write a futures contract on S, the formula we developed for futures prices last week was that you take the conditional expected value under the risk-neutral measure of the final price conditioned on the time of pricing. And because at the final time S and R are the same, that's the same as taking the conditional expected value of the interest rate at capital T. And the interest rate at capital T is given right here in this equation. And if I put that in, R of capital T, it's equal to R of little t plus A of capital T minus little t plus sigma of W tilde of capital T minus W tilde of little t. And the reason I've chosen to write it in this way in terms of R of little t is so I can do this conditional expected value easily. R of little t is F little t measurable, so it comes out of the conditional expected value. This term is not random, A of capital T minus little t. And this term is independent of the sigma algebra and also has mean 0, and so it goes away. So I get this formula for the futures price of my contract. And if I take, let me call this simply F of t so I don't have to keep writing the whole long thing. If I take the differential of F of t, I get dr of t minus a dt, right? This differential with respect to the little t variable, which has a minus sign on it here. And if you look at dr of t minus a dt, here it is. It's written with a u there, but it's the same thing. If I had dr of t minus a dt, then the difference would be sigma dw tilde. So this is sigma dw tilde of t. And we see that the futures price is a martingale. There's no dt term on the right-hand side. That's the way it should be. Futures price is a martingale. Now suppose I'm going to create a portfolio, and my portfolio will, first of all, x of t will be the portfolio value. And delta of t will be the number of futures contracts held by the portfolio at time t. And finally, t delta t, so the trading in futures is financed by the money market account. It doesn't cost anything to buy a futures contract, but if you buy a futures contract, you have to set up a margin account, and if you get a margin call, you have to put money into your margin account. Or if your futures position is doing well, the exchange is putting money into your margin account, and you can take some of it out. And what I'm assuming here when I say financed by the money market account is that there's the interest rate process given by the Ho and Lee model, the interest rate process that we see over here. And on both the margin account and anything else that I have in cash, I'm going to get the interest rate. Or if I have to borrow money to put into the margin account, I borrow it at the interest rate that we're seeing over here. So then I want to write down how does the value of this portfolio evolve. So what does dx of t look like? And I'll start the process off. I'll say, well, if you have at time t, you have a position in futures delta of t. When the futures price moves, you get a profit or loss from that. It goes into or comes out of your margin account. And then we're financing all of this by the money market account. And so here we put a term r of t. And then I'll tell you, there's a trap lying right here. X of t. What else do you think we should put? The reason I want you to fall into this trap is, if you do it now, it's completely harmless. It's a little bit embarrassing, perhaps. But everybody falls into the trap, so you shouldn't be embarrassed. And if you fall into the trap now, you won't do it next Tuesday evening, right? So what should we put next? What would we put if we were investing in a stock? We'd have ds of t here, right? And what would we have here? Yeah, it would be the value. This would be the total value of our portfolio, and we'd subtract off how much is in the stock, delta of ts of t, and then the difference would be cash, and that's what would be getting the interest rate. Do we want to do that here? Do we want to write here, do I want to write minus delta of t, f of t?
No, because you don't pay anything for the future.
Excellent. No, don't do that. This is not the price of money that's tied up in the futures contracts. You don't pay anything for the futures contracts. All the money is in cash. It's either in your margin account or it's in your bank account, but you don't have any value tied up in the futures contracts. They have value 0. So don't fall into this trap next Tuesday. So how does this go then? Delta of t, differential of futures is right here, sigma dw tilde of t plus r of t, x of t, dt. To get rid of this mean rate of return r, we discount, and that will take this term away. I've said this several times, and I'll say it again in the future, but for once let me actually do it again carefully, why it is that how discounting works on this equation. So the discount process that we're using here, capital D of t, is e to the minus 0 to t of r of u du. And if you take the differential of that, well, you have to differentiate the thing that sits in the exponent, and there's a minus up there, and then the fundamental theorem of calculus says you'll get an r of t, and that's a dt term. And then whenever you differentiate an exponential, you get the exponential back again, and the e to the, right, you get this whole thing back again, and that's d of t. So if I discount the portfolio value and take its differential, I will get x of t times the differential of the discount process plus d of t times the differential of the portfolio. And I don't need to worry about the extra term, the product of differentials, because the differential of the discount has no dw tilde in it. This term, using the differential of the discount, is minus r of t d of t, and then there's the x of t dt, plus, and here I have the discount, and since I'm running out of room, let me drop the t's and just write this down. At the differential of x, I have delta sigma dw tilde plus rx dt. And so the whole point of the discounting was to kill that term, and you see it cancels with this term. So this rx discounted dt cancels here. And so what we get is d of t, delta of t, sigma dw tilde of t. And in the past and in the future, whenever I'm seeing something like this, I say, well, if I want to kill the rx of t dt, I will discount. And the effect of that is to remove this term, and the other term remains, but it has a discount factor multiplying it after we do the calculation. So I won't do those anymore. I'll just say that, and we'll go ahead. Okay, so there's the evolution of the value of a discounted portfolio. Let me consider a caplet, an interest rate caplet. R of capital T minus K, positive part at time capital T. The idea of this is the following. So first of all, let me talk about an interest rate cap. If you have a mortgage and you're paying the floating rate, you may want to get a cap which says that each month I pay whatever's the floating rate on my principal, but I never have to pay more than 10%. So that never have to pay more than 10%, that's a cap. If in one of the months the floating rate is 12%, you only have to pay 10 by, you should be paying 12, but you're only paying 10, and so you're forgiven that extra 2%. So the amount that you're forgiven is the actual minus the cap of 10%. So this is the value of the cap in that month in which the interest rate is above 10%. And a cap has a bunch of those, right? Every month you get to apply the cap. If the interest rate is above the cap, you get to be forgiven the difference. A caplet is just one of them. So I'm looking here at a caplet that just pays just one of these payments. And actually the caplets are not quite written on the instantaneous interest rate. They're written often on the LIBOR, a little bit of a flaky interest rate. We'll talk more about that in the second half of the course, but let me tonight just price a cap on the instantaneous interest rate just to get us warmed up to this idea. And then we think about, well, how much is this worth at times prior to the payment date? And so the price of the cap at time t, where t comes before the expiration date, is, well, you have to discount. So it's going to pay at time capital T. You take that payment and discount it back to little t. And here is the payment. And you take the risk-neutral conditional expected value of that. And because our interest rate process is a Markov process, and everything that sits in here involves the interest rate process after time little t, when I condition on all the information up to time little t, the only thing that's relevant is the interest rate at time little t. And so this will turn out to be some function of t and r of t. This function satisfies a partial differential equation, and in fact it's the same partial differential equation that we saw for S, this partial differential equation, and the reason is because the discounted cap is a martingale. If I look at the discounted cap, this is not a cap, this is a caplet. And if I looked at the discounted caplet price, this would be, when I multiply this by d of little t, I can take it inside the conditional expected value because d of little t is f little t measurable, and it completes the discounting. Right, here's discounting from capital T back to little t. D of little t is from little t on back to 0, and so the product of the two gives me discounting all the way back to 0. And if you look in here, there is no little t. And once I get the little t, then I can use the Tower property and show that I have a martingale. Once you have a martingale, you do the four-step procedure and set the dt term equal to 0. This is a martingale. This is a martingale. So the four-step procedure is going to go the same way on this page as it did on that page. And so what you're going to find is that this function c satisfies the same partial differential equation as on page 1. So c satisfies the PDE on page 1. Also, it has a terminal condition that's different from that PDE. At the final time, the value of c is r minus k positive part for every r. I didn't say it over here, but over here the terminal condition is at the final time S agrees with R, and so this is equal to R for every R. Okay, so we could go out and we could numerically solve for this function c. Later this evening, I'm actually going to solve analytically. If you think about what C is, and you think about what is the distribution conditioned on f of t, of r of capital T, and this integral, with some work, several pages of calculation, we could produce it here. I'm not going to do that right now because I'm going to show you an easier way to do it than brute force later on this evening after we do a change of measure argument. Okay, so far so good? All right, well, in the spirit of Black-Scholes, we would like to replicate the caplet, but we're going to do it by trading in futures rather than trading, right? We have our choice here. We could trade in the asset S, or we could trade in the, well, these are essentially euro-dollar futures that we've computed here. I guess I don't have my futures calculation visible here. Or we could trade in the futures. The futures are more liquid and so we'll trade in the futures instead. So we want to replicate the caplet by trading in futures. Interest rate futures. We already see how the value of our replicating portfolio is going to evolve. The discounted value of the replicating portfolio is given by that formula. We have to also look at the discounted value of the caplet price. Whoops, I can't do that. So I need to look at the discounted value of the caplet price. So the product rule says you will get the caplet price times the differential of the discount process plus the discount process times the differential of the caplet price. And I don't have the third term because the differential of the discount process doesn't have a dW tilde in it. This, the differential of the discount process, we did over here. It's minus r times the discount dt. So actually I'm going to get a discount process in every term. Let me factor it out. And then the rest of what's here is a minus r, and then the caplet price dt. This discount process has been factored out, and then I have to take the differential of the caplet price, and Ito's formula says c sub t dt plus c sub r dr plus 1/2 c sub rr dr. Dr is a dt plus sigma dw tilde. So that goes in for dr. And dr is the square of that. So that's just sigma squared dt. The dt terms altogether give you a 0 because the discounted caplet price is a martingale. So we know the dt terms are going to give us a 0. Or another way of saying the same thing is that we said that C satisfies the partial differential equation on page 1. And if you look at that partial differential equation, it says that exactly the terms we have here, minus r times the function, then the time derivative, and then a times the derivative with respect to the interest rate, and then 1/2 sigma squared times the derivative, second derivative with respect to the interest rate. All of those add up to 0. So the dt terms are all gone, and I'm only left with this dw tilde term right here. So I get d of t sigma, I have a c sub r. Let's see, is that everything? Sigma c sub r dw tilde. So if we want to replicate, we want the differential of the discounted portfolio to agree with the differential of the discounted caplet price. And if you look at those two formulas, they're exactly the same, provided that we set delta of t, our position in futures, to be the delta of the caplet price, the derivative of the caplet price with respect to the interest rate. So take delta of t equals c sub r of t and r of t. And that's all very satisfying, right? It looks a whole lot like Black-Scholes. I should warn you at this point that the formula is not always that simple. And in general, the futures price is going to be some function of t and r of t, and the delta is going to be the ratio of the delta of the caplet price with respect to the fraction of the delta of the futures price. In the particular case that we're working in here, where is the futures price? Right here's the futures price. And so if you said the futures price, here's the futures price. If you said the futures price is a function of t and the interest rate, the futures price is a function of little time and the interest rate, and that function of t and r is just r plus a times cap t minus little t. And so the derivative with respect to r of the futures price is 1. And so we didn't see it in our formula. We didn't see it show up because it's a 1. So let's go back and just do that slight modification so that you can see that happen as well. So in general, the future is the risk neutral conditional expected value of the interest rate conditional on the information at time little t. And as long as your interest rate is a Markov process, then this will be a function of little t and r of little t, where this function satisfies a partial differential equation. Then when you look at the value of your portfolio, delta of t df of t plus r of t x of t dt. What is df of t? Well, you have to take this differential here. Actually, let me write one extra step here. Right? We'll have to take this differential. And so that will be delta of t. We'll get a time derivative of f dt plus a f sub r dr plus a 1/2 f sub r dr plus an r of t x of t dt. Now, let's assume for the interest rate. So I didn't say, I mean, we did the case of Ho and Lee, but in general, the model for the interest rate would look like this. dr of u is some function beta of u and r of u du plus some other function gamma of u and r of u dw tilde of u. And so when we get to this point, we fill in for dr, we fill in beta dt plus gamma dw tilde, and so we're going to get dx is delta f sub t dt plus, and then as I say for dr I fill in beta dt plus gamma dw tilde and then 1/2 f sub r. Dr is gamma squared dt and we're not going to get a dt term. Why is that? The futures price is a martingale, right? This, we can see that using the Tower property, you can see this is a martingale. So the dt term is going to vanish here. That gives us a partial differential equation. I have messed up, haven't I? F sub r right here. That gives us a partial differential equation for the function f, the one that says the dt term vanishes. That would be f sub t plus beta f sub r plus 1/2 gamma squared f sub r is a 0. And once it's gone, the only term left is right here. I did not finish my dx, though, because dx also has an rx dt in it. And so I get dx is equal to delta gamma f sub r dw tilde plus rx dt. This is what we got in the Ho-Lee model. If you go back and look at it, our f sub r was a 1, and our gamma was the number a, and I hope that's what we got. Dx, I'm sorry, our gamma was a sigma. Where's dx? There it is. Delta, our gamma was a sigma. F sub r is a 1, dw tilde plus rx dt. Right? So this, and then discounted x is discounting kills the rx dt term, and it multiplies the other term by the discount process. So we'll get d of t, delta of t, gamma of t, r of t, f sub r of t and r of t, dw tilde of t. So in general, well, general one-factor model, this is the way the portfolio would evolve if we're trading in futures. And what would happen to the way that the value of the caplet evolves? The only difference is this formula here is still correct, except that when we plugged in these values for dr, we should have been plugging in the more general case right here, general functions beta and gamma. And so if I do that, go back and make that change. So the differential of the discounted caplet price equals d of t, and then I have minus rc dt plus c sub t dt plus c sub r, and now here we have a function beta dt plus another function gamma dw tilde plus 1/2 c sub r. Dr is this thing squared, so that's gamma squared dt. The discounted caplet price is a martingale, so all the dt terms will cancel. Right? C will satisfy the right partial differential equation, and so what we're left with is the dw tilde term. So we'll get a d sub t, we'll get a gamma, and that will be evaluated at t and r of t. We'll get a c sub r, that will be evaluated at t and r of t, and a dw tilde of t. That's what we got before, except in place of a gamma we had a sigma. And so that's exactly the formula we had before. And now if we compare this expression to the hedge portfolio, the differential of the discounted replicating portfolio, if we're going to get them to agree, we need the gamma to be the ratio of C sub r over C sub f sub r. So I said gamma, but I mean delta. You need the delta, the number of shares, the number of futures contracts you hold at each time t. You need to be C sub r over t and r of t divided by f sub r of t and r of t. That's the general formula.
Professor?
Yes.
So the function little f, is it always 0?
Is the function little f, is this always a 0?
Well, I mean, I guess in that equation that you just pointed, there is an RF term, right? I mean, if from last lecture, if f is not the future process in general, we will have an RF term, right?
If the function f is telling me the price of some tradable asset, right? If it's the price of some asset, then discounted f will be a martingale, and so there will be a minus RF in this equation in addition to the terms that you're seeing here. But in this particular case, the f is standing for the futures. This is already a martingale undiscounted, and so you don't see the minus RF term because I don't put any discounting in here to get a martingale. The undiscounted version is the martingale. Have I answered your question? So when we're looking at caplet prices, or even this contract we began with initially, so when you're looking at this contract we began initially, the contract that pays R of capital T at S of capital T, that's an asset, and it's the discounted asset price that is a martingale. So if I represent that asset as a function of time and the interest rate, that function will satisfy a PDE that has a minus R times the function in it, just like Black-Scholes. But if I'm looking at the futures price undiscounted is a martingale, and so the equation for the futures price is missing that first term. That minus RF is not in the function for the futures price. And you notice that we don't want it to be because the discounted portfolio value turns out to be a martingale. Here it is. The discounted portfolio value turns out to be a martingale. I need these, to get that to work, I need this equation to hold. When I take the differential here, I needed these dt terms to vanish, and the dt terms were exactly this. And it's always, what we're always after is making our discounted portfolio, our discounted replicating portfolio, that's what we want to be the martingale. Okay, so I've maybe talked all around it. Let me see if I've answered your question.
Yeah, that was helpful.
Okay. Okay, let me then change gears slightly and introduce the topic of change of measure, but we won't get very far because we're coming up on our first break. So I'll remind you of section 5.2.1, where what I'm about to call M was called Z. And it's too late for you. The afternoon class yesterday already confessed that Scott Robertson covered this. So I will go through it fairly quickly and then see if you have questions rather than spend a lot of time on it. So the story is this. We're going to be given a probability space, an omega, an F, and a probability measure, and a strictly positive martingale. M that starts at 0. I said that wrong already. Starts at 1 at time 0. And whenever you have that situation, you can create a different probability measure. You can define P tilde of A. So given a set A, you integrate over A M of capital T dP. The reason we want M of capital T to be 1 is because we want P tilde of all of omega to be 1. And by this formula, P tilde of all of omega is the integral over capital omega of M of capital T. That's the expected value of m of capital T. And m is a martingale, so its expected value cannot change over time. So that's m of 0, and we want that to be 1 so that we can call p tilde a probability measure. And the notation we generally use just to shorten this is we write dp tilde over dp is m of t. And we call this m of t the Radon-Nikodym derivative. Of p tilde with respect to p. You know what's going on here, Jordan? The projector keeps going in and out. Actually, is it happening to you in New York as well, or just here in Pittsburgh? The secondary projector sort of comes and goes.
We're fine. I don't think we see anything.
Great, great. Okay. All right, so my way of thinking about this is that m of capital T is a random variable that's strictly positive. So for each omega, this is a positive number. And what it's doing is omega by omega, it's adjusting probabilities. There's a p probability for that omega. You multiply it by m of capital T, and you'll get a p tilde probability for that omega. And if m of t is bigger than 1, then the probability goes up. If m of t is less than 1, the probability goes down. That's intuitively what's going on, but what I just said is nonsense, because when we're in these infinite spaces, the p of each omega is 0. And so we can't think about taking the p probability of omega and adjusting it up or down by multiplying it by numbers bigger or less than 1. And what this statement is saying is, well, so you can't do it for individual omegas, you do it for a set of omegas. So take a set of omegas so that you can see some probability. And then if m of capital T is bigger than 1 for every omega in that set, then the p tilde probability of that set of omegas will be greater than the p probability. And so set by set, you're adjusting probabilities up or down. But I think it's sometimes helpful to sort of pretend that you can do it for individual omegas. M capital T of omega tells you whether things are going up or down. There are two lemmas that I want to write down before we take the break. That we use to operationalize this notion of change of measure. And for those lemmas, we take 2 times 0 less than or equal to s less than or equal to little t less than or equal to capital T. And we assume that a random variable y is f little t measure. Then, if you want to take the p tilde expected value of y, you can do that by taking the p expected value, but you have to adjust the probabilities of omegas, and so you can use m of capital T to do that. But since y is f little t measurable, you don't really need to use the m at capital T. You can use the m at little t, and that will also give you this same answer. The first equality here starts from this statement. This statement says that if y is an indicator function, if y is the indicator of A, let me put omega here, which is the random variable that is a 1 if omega is in A, and 0 if omega is not in A, then this statement right here, 1, and this statement right here, 2, are the same. So 2 is just the definition of the probability measure p tilde. right? Because if you take the expected value under p tilde of this random variable, you will just get p tilde probability of A. That's the left-hand side. And if you take the expected value under p, multiplying m by a random variable that is 1 whenever we're in A and otherwise is a 0, you're really actually taking the integral just over the set A, not over all of omega. And once this equality works for indicator random variables, you can argue that it's going to work for every random variable because you can put random variables together by sums of constants times indicators and then pass to a limit to get everything. This thing, we'll call it 3, is iterated conditioning. In fact, if you take the expected value of y given m of capital T and condition that on little t, condition on little t, right, so that equality is just the fact that the conditional expected value, the expected value of a conditional expected value is the unconditional expected value of the same thing. We've assumed that y is f little t measurable, so we can take it out. And we're also told that m is a martingale. And so once I just have expected value of m of capital T given f of little t, that knocks back to m of little t. And so I have expected value of y m of little t. So this first pair of equations, this is lemma 5.2.1. This is easy to verify that this is right. We can talk about the intuition here in just a moment. The second lemma is the same setup. So we still have a y that's f little t measurable, and I'm trying to take a conditional expected value of y given f of s. Rather than an expected value. And I want to switch that back to a conditional expected value. Oops. I want to switch that to an expected value under the original measure, conditioned on f of s.
Can you move the paper down a little bit, please?
That would be a good idea, wouldn't it? Okay. I want to condition that on, write that as an expected value with respect to the original probability measure, conditioned on f of s. And it's no surprise that you multiply by m of little t, just as we were doing in this equation. What's a little bit of a surprise is you divide by m of little s. And my intuition for this is the following, that if you were to think about a path, so here's capital T, here's little t, here's little s, and you think about a path, and again, the p tilde probability of this path is 0, but let's think about the p probability. And the p tilde probability is m of t times the p probability. Doesn't quite make sense because both those probabilities are 0. If you multiply by m of t, you don't know m of t, capital T, until you get to here. And what happens if you multiply by m of capital T, you will adjust the probability along the whole path. Of course, if you have a random variable that only depends on the path up to time little t, you don't need to worry about adjusting the probabilities on this path. And so m of little t would work because m of little t adjusts the probability between here and little t. And if you're taking a conditional expected value, condition on f of s, you're already sitting at here, and you only need to adjust the probability on the piece of the path between s and t. And for doing that, you would take m of little t over m of s. M of s will adjust the probability from 0 to t. Dividing by m of s cancels away the initial part, and this adjusts the probability on the piece of the path between s and t. If you do this in a binomial model, it works exactly like this. Because what happens in a binomial model, you have up steps and down steps, and you have a p probability of an up step and a p tilde probability of an up step. And the m will adjust link by link, but m of will adjust on all the links between 0 and t. If you divide by m of s, then you'll find that what's left adjusts just on the links between s and t. And so that's why this m of t divided by m of s shows up here. I've written the m of s on the outside, but of course I can move it in because we're conditioning on f of s. Okay, let me pause here and invite questions before we go to break. Is there, so I proved equations 2 and 3. I'm not planning to prove 4 because the proof of 4 is hard. And the guys on Monday afternoon said that Scott Robertson proved 4 for you. So I don't have any more to say unless I'm prompted by a question at this point. Any comment? All right, shall we take 10 minutes and then come back and we will see how we use this to change measure. Okay, we're back. Let me pick up my favorite pen here. So I would like to talk about quotients of martingales. A point that I should have made before the break, but I guess it's not too late to make it, is that when I'm talking about changing the probability measure here, and so we have a martingale M, and we use M to change the measure. And I've used the notation here that we use when P is the actual measure and P tilde is the risk neutral measure, but there's no reason that it has to be that way. P could be any probability measure, and as long as M is a strictly positive martingale satisfying M of 0 equals 1 under the probability measure P, then I can change and get a different probability measure, which I'm calling P tilde here, but if P is not the actual measure and Z is not the right rad-on negative derivative, then P tilde doesn't need to be the risk neutral measure either. Certainly the example that we have that you've seen and we spent a lot of time with, or you and Scott have perhaps spent a lot of time with, is the case where the M of t is the minus theta w of t minus 1/2 theta squared t that's used to change from the actual to the risk neutral measure. But again, this idea works more generally. It doesn't have to just be from the actual to the risk neutral measure. And we will use it more generally. What I'd like to do with it right now is think about a quotient of martingales. And you will find in section 9.2. So let's suppose that S and N are asset price processes. And positive. So that means that if we work under the risk neutral measure, discounted S and discounted N will be martingales. D of t, S of t, and D of t, N of t are P tilde martingales. And I'd like to think about a quotient, Q of t, which is S of t over N of t. And the reason I'd like to think about that is because we often want to change the units in which we're keeping account. S might be, for example, S might be the price in dollars of IBM stock. And I guess that shows how old-fashioned I am. S might be the price in dollars of Facebook stock. And N might be the price in dollars of a euro. And if I divide S by N, I get the price in euros of Facebook stock. So this quotient here is actually the way one would change the currency. And there are other changes that we will want to make as well, besides just changes of currency. So it often comes up that we want to price one thing in units of another, and you do that by dividing their prices. And so you wind up looking at a quotient. And this is really a quotient of martingales, because I could write it as the quotient of discounted S of t over discounted N of t. And this is hardly ever a martingale. So this is not a P tilde martingale. And part of the moral of the story is that if you change currencies, you're going to have to change risk neutral measures, because even though you may have had a risk neutral measure that worked when you were denominating in US dollars, if you divide like this and denominate in euros, the risk neutral measure that you're using will no longer be risk neutral. and you're going to have to change measures in order to find a risk-neutral measure again. And we'll use this construction that we were doing before the break to do that. In one of our undergraduate classes, there is a module on foreign exchange, and on one of the exams, one of the students once wrote a very nice essay about how mathematics is the same on this side of the Atlantic as on the other side. And so if something's a risk-neutral measure on this side, it'll be a risk-neutral measure on the other side, and that's just utter nonsense. If you change the units of currency, you have to change the risk-neutral measure. And what I would like to think about is how can we make Q be a martingale? So under what measure is Q a martingale? And the answer is surprisingly simple. In order to change the measure, we need to have a positive martingale, as we were discussing on this page. What I do for my positive martingale, m of t, is you take the numeraire. The numeraire, I call that the numeraire because what I'm doing is I'm denominating s in units of n. So I think of n as the numeraire, the units of account. Now, you should object and say, n is a p tilde martingale, and m has to be a martingale. So, okay, let me discount it so it becomes a martingale. And then you might still object and say, but I need m of 0 to be 1, so when I change the measure, I get a probability measure. And so I'll say, all right, so divide it by n of 0, so that at times 0, it's equal to 1. D of 0, of course, is 1, so this will be 1 at times 0. So the way I remember this is I say, I want to take the numeraire to be my positive martingale that starts at 1, and the numeraire isn't quite that, so I fix it up in the obvious ways, discount it and normalize it, and use that. So here's the claim. So I'm going to define P tilde, I'll call it Pn because I'm using the numeraire to change to it by specifying that Pn of a set A is what I get when I integrate over the set A d of cap t, n of cap t over n of 0 dp tilde. Okay, so we are now changing, but our base measure is risk neutral, and we're moving on to some other measure, which I'm calling Pn. And my claim is that under Pn, Q is a martingale. I'm going to give you a short proof and a long proof. The short proof, it's embarrassing if you only know the long proof and somebody asks you to prove this and you give them the long proof, because then they can show you the short proof and it's essentially a one-liner. So you want to know the short proof. But I'm reminded of a quote by Herman Weil, a mathematician, and I can't quite remember the quote, but it was something of the effect about how you have some problem and you work really hard on it, and then a mathematician comes, your problem is you're trying to get through a door and the door is locked, and you work really hard on it and you can't do it. And along comes the mathematician and he says, here's the key, and he sticks it in and he opens the door. And what the mathematician doesn't tell you is that before you came, he tore the lock apart and discovered how it works and designed the key. So this proof is, here's the key, I'll open the door. And then after we do this, we'll tear the lock apart and understand exactly what's going on. So here's the slick proof. So we want to show Q as a martingale, so we consider 2 times. I already have a process S, so maybe I'll call this time U, less than or equal to little t, less than or equal to capital T. And I'll look at the En measure of Q of t conditioned on f of s. And of course, I want to get Q of s, right? That's the martingale property. Equals. All right, so Where's our second lemma? Where's page 8? Here tells us when you have a new measure, EN, and you're taking a conditional expected value and you want to go back to the old measure, which in our case is the risk-neutral measure, E tilde, then you should multiply, right, Q of t as our FT measurable random variable. You should multiply Q of t by M of t and divide it by M of s, and then take the conditional expected, whoops, I said I was going to use U there. U, just because I have a capital S in my calculations and I don't know how to make my little s's look different from my capital S's. So I'll use a U. And now it's all over. Now you can finish it on your own. As I was doing this yesterday afternoon, I was reminded at this point of the story in David Hilbert's biography. David Hilbert was one of the great mathematicians of the 20th century, a German. And he was in Göttingen in Germany at the time the Nazis came to power. And most of his other mathematicians were Jewish, and they left, and he was left there by himself, and he was not very sympathetic to the Nazis. And he was one day giving a lecture in class, and you have to know who the Prussian officers were. So when Germany was united in the 1860s, it was united by the principality around Berlin. Berlin was the capital of Prussia, which was that one principality, and the Prussians then became the officers in the German army. And so Hilbert was giving this lecture, and he was doing some problem, maybe not this one, and he got to a point and he said, and now it's so simple that even a Prussian officer could solve it. And this created quite a stir. The Nazis were pretty upset that he said such a thing because he was a famous mathematician, and they demanded that he retract. And so the next day when he was giving his lecture, they came. So there's all these people sitting in the back of the lecture hall waiting to see what he's going to do because they've demanded that he retract. And so he said, last time when I was giving my lecture, I got to this point and I said, now it's so simple that even a Prussian officer could solve it. That, however, is not the case. So whether a Prussian officer can solve this or not, let me go ahead and finish it for us. So I'm just going to follow my nose, and where I have a 1 over m of u, I will take this, I'll turn it upside down, and I'll replace t by u. So turn it upside down, and I get n of 0, d of u, n of u, e tilde. What is q of t? There it sits. I'm going to write it this way. D of t, s of t, over n of t, over d of t, n of t. And then m of t, d of t, n of t, n of 0, conditioned on f of u. Okay, so what would our Prussian officers do here? So we can cancel the d's, right? And we can cancel the n's. And the n of 0 is just a constant, so the n of 0 outside will cancel the n of 0 inside. Okay, and this one may be too hard for the Prussian officers. What's the other thing we need to do? How this? Martingale property, right? Discounted price is a martingale, discounted S is a martingale under the risk neutral measure. And so using the martingale property, this becomes d of u, s of u. The d's cancel. I get s of u over n of u. And that is, in fact, q of u. Right? And so there's our martingale property. I don't like this proof, as I said, because it's too slick, and you don't really see what's going on. So let me give you the long proof of the same thing. So it's an asset. And what does that mean? Well, that means that if you look at the differential of S, it will be the risk-free rate times S of t dt, and then S of t, and then there will be volatility times Brownian motion. We're going to use this in models in which we have more than one Brownian motion. So right here I'm going to write a sum. J goes from 1 to d of sigma j of t dw j tilde of t. So these are independent Brownian motions under the risk neutral measure p tilde. And these are adapted processes. And the summation notation will get out of hand if we're not careful. So I'm going to create some vector notation as well. So I can also write this as R of t, S of t dt, plus S of t, sigma of t dot dw of t, and that's a dot product, w tilde of t, that's a dot product between two vectors, right? So the sigma of t is the vector sigma 1 of t up to sigma d of t, and the w tilde of t, or dw tilde of t, is the vector dw tilde 1 down to dw tilde d. And so I'm writing this sum as a dot product. If we look at the discounted stock price, well, it's what we said before the break. The discounting kills the risk-free rate term, and it multiplies the other term by d of t. So I have d of t, s of t, sigma of t, dot dw tilde of t. And the solution to this stochastic differential equation, well, maybe I shouldn't call it a stochastic differential equation because I have things here that are random on the right-hand side that are not d and s, d times s. The solution of this equation is that the discounted stock price at time t is equal to the initial discounted stock price exponential, and then you will have the integral from 0 to t sigma of u dot dw tilde of u minus 1/2 0 to t the Euclidean norm of sigma of u squared du. Let's see. Yeah. This is exactly the exponential martingale. In the scalar case, you just have sigma dw and 1/2 sigma squared du. And when you do it in the multidimensional case, because these Brownian motions are independent, it turns out that it's just a dot product here. And you could write this as sigma dot sigma there if you wanted to, right? It's the sum of the squares of the sigma j's. If you don't believe that, just use the multidimensional Ito formula and take the differential of this, and you'll come back to the line above. So we have two processes. We have the S and we have the N, and the N will be of the same sort. Let me write just the differential form, the discounted form. So that will look like d of t, n of t. And then there will be some vector of volatilities, just like this vector of sigmas. There will be a vector of volatilities, and I'll call them nu, dw tilde of t. Let's see, I don't know why I wrote d of 0, because d of 0 is 1. And then the solution to this is d of t, n of t is n of 0 exponential 0 to t nu of u dot dw tilde of u minus 1/2 integral 0 to t Euclidean norm of nu of u squared du. And we want to take a quotient. So if I divide d of t s of t by d of t n of t, I'll get s of 0 over n of 0. That'll be q of 0. And then in the exponent, so what do we get here? Well, I'll get these terms. So I'll write that like this. There's an integral from 0 to t, and then there will be sigma minus nu dot dw tilde, and minus 1/2 0 to t norm of sigma squared minus norm of nu squared du. Okay, let me pause and see if there's any point that you want to be further explained, right? We're taking the lock apart here, and it's getting a little bit messy. So let me see if there's any part. First, I may have a mistake, and even if I don't have a mistake, there may be a part that needs some explanation. Let me see how we're doing. Any questions?
Is it Q0 times exponential or equal exponential?
See, there is a mistake, isn't there? Thank you. So this should be a times. Thank you. Anything else? We would like to find a martingale. And if you think about this, okay, what I have here is Q0 and then times, and I have 0 to t sigma minus nu dot dw tilde minus 1/2. And what sits over here I could write as sigma dot sigma minus nu dot nu du. But if you're going to have an exponential martingale, what you should have is, if you're going to have a sigma minus nu there, then what you should have here is minus 1/2 integral 0 to t of sigma minus nu dot sigma minus nu du, right? That much by itself would be a martingale. And whatever is here, multiplying the Brownian differential of the Brownian motion, you see the square of it there integrated with respect to time. But that's not what we have. So we have to pick up the extra terms. So what are the extra terms? Well, we subtracted this out and we didn't really have a right to, so now I have to add it back in. Plus 1/2 integral 0 to t sigma minus nu dot sigma minus nu. And then what we had is still there, so let's write it down. It's with a minus sign. So it's a minus sigma dot sigma plus nu dot nu. Let me pause for a moment and see if you agree with my calculation. So what I did was, I said if I have a sigma minus nu here multiplying the differential of the Brownian motion, then I need 1/2 the square of that here, sigma minus nu dot sigma minus nu. I just put it there, but then I have to cancel it away. So here I am canceling it away. And then what was really there was a minus 1/2 sigma dot sigma. So there's the minus 1/2 sigma dot sigma. And this is actually a plus because of these two minuses, a plus 1/2 nu dot nu. So here it is plus 1/2 nu dot nu. Okay? So let's go on to the next page. Put that where everybody can see it. So Q of t is Q of 0 exponential integral 0 to t minus nu dot dw tilde minus 1/2 integral 0 to t sigma minus nu dot sigma minus nu du times the exponential 1/2 integral 0 to t And now let's multiply this one out. So if you multiply that out, you'll get a sigma dot sigma. You'll get a cross term, a sigma dot minus nu and a sigma dot minus nu, so you have two of them. So minus 2 sigma dot nu, and then you'll get a nu dot nu. And then we have a minus sigma dot sigma and a plus nu dot nu. So that is that. And so what we have in here is, well, we have two of these. So we have a 2 nu dot nu and a minus 2 sigma dot nu. There's a half out front. And so altogether, we have the first sigma minus nu dot minus nu du dot exponential 0 to t. The half kills the 2's, and I have a nu times nu minus sigma du. Let me see if you agree with my algebra, first of all. It's okay? This is an exponential martingale. So let me call it m of t for martingale. And this I will call a of t. If we take the differential of dm of t, what you will get is m of t sigma minus nu dot dw tilde. It's the usual Ito formula thing. Here you get sigma minus nu dw tilde when you differentiate this. You're also going to get that term, but then when you do the second derivative in Ito's formula, it kills that term. And so you get just a dw tilde. This one's a martingale. This one, dA of t, if you differentiate that, you'll get the a of t back again, and then you'll get, I'm going to write this as a minus nu, a minus sigma minus nu dot sigma dt. Okay, so this one, when I differentiate, it's just ordinary calculus because that's an integral there, so it's nice and smooth. And I'll get this whole exponential back again, that's the a of t, and then I'll get the derivative of this, which is nu times nu minus sigma. I've turned this around and written it as sigma minus nu. Whoops, I made a mistake here. Nu. This one I've turned around and written as sigma minus nu. That's right, there's a minus sign here, times nu dt. And so the differential of dq, well, there's q of 0 sitting out front. And then the product rule says you get m dA plus a dm. And I don't have to get the third term because dA doesn't have any dw tilde in it. So we get q0. M dA is minus m a sigma minus nu dot nu dt. And a dm is m a sigma minus nu dw tilde. Q0 times m times a is q of t. So that's what I have here, right? Q0 times m times a and Q0 times m times a. So you get q of t. And then what do we have here? I have a sigma minus nu dot dw tilde minus nu dt. and that's the end. Okay, let me see if anybody got lost. Is there anybody still out there wandering around? Or are we all time to gather up the group here? Have we all gotten to this line? Any questions? How did you get from there to there? Well, we see that Q is not a martingale, because if it was going to be a martingale, we would have only gotten a dw tilde, and in fact we got dw tilde minus nu dt, right? So not a martingale, at least not under p tilde that makes this be a Brownian motion. But we know how to change measures, and let's think about how we do that. Let me remind you of Girsanov's theorem. With Girsanov, you have W, which is a Brownian motion under P. You have W tilde. dW tilde is theta dt plus dW. You want to change to the measure so that W tilde is a Brownian motion. And so you define a process Z of t, which is exponential of minus integral 0 to t of theta dW minus 1/2 the integral from 0 to t of theta squared dt. And then you define p tilde using z to do the change of measure, z at the final time capital T, and under p tilde, W tilde is a Brownian motion. I've written it as if it's one-dimensional, but it could just as well be multidimensional. This could be a vector of thetas, and this could be a norm of theta squared, and everything would still go through. I start with a vector of Brownian motions W, and to each component I add on a theta. Right, so I have a vector of thetas, and then after I do the change of measure, W tilde is a vector of independent Brownian motions. If I start with a vector of independent Brownian motions, I get a vector of independent Brownian motions. In the calculation that we were just doing, we started with W tilde, so this was a vector of Brownian motions under P tilde. When we get to the end of our calculation, we don't see a dW tilde by itself. We see a W tilde minus nu dt. And so I'm going to give that a name. I'll call that Wn. So dWn is dW tilde minus nu dt. I'd like to change to a measure that makes that be a Brownian motion. If I could change to that measure, then I could just write this as Q of t sigma minus nu dot dWn, and it would be a martingale under the measure that makes Wn be a Brownian motion. So what do I use for my Z of t? Well, we follow the formula here. So when we were adding a plus theta dt, we had a minus theta here. Here we have a minus nu dt, so I'm going to get a plus nu here. So I'll get here 0 to t nu dot dW tilde, right? Because we're starting with a Brownian motion W tilde under P tilde. And so we use the W tilde, the Brownian motion we started with, minus 1/2 integral 0 to t of norm of nu squared du. This should be a du. So have we seen that before? There it is, right? It's exactly that. Right? This is exactly that. So this is d of t, n of t, over n of 0, right? Put the n of 0 on the right-hand side. So we're using the numeraire discount normalized, so it's a martingale starting at 1, and that's going to play the role of our Radon-Nikodym derivative. And so the probability measure we get is the one we called Pn, which uses d of cap t, n of cap t over n of 0 to do the change of measure. Okay, so what have we learned by tearing apart the lock? Well, we've learned two things. So we already knew that this was the Radon-Nikodym that was going to change the measure so that the Q was a martingale under the new measure. So that was not new. But one thing that we've learned that's new is how to get the Brownian motion under the new measure. And what do? You take the volatility vector. Now I'm doing a multidimensional Brownian motion here, and so my numeraire process has a vector, right? The volatility is not a scalar, it's a vector. D, right, nu 1, nu 2 up to nu d. You take the volatility vector and you take each component of the nu and subtract it off of the corresponding component, right? Integrate the nu with respect to time, subtract it off the corresponding component of the Brownian motion. And this will give you the Brownian motions under the new measure. New sort of with two meanings there. So what I'm saying is that W in J of t is W tilde J of t plus the integral from 0 to t of nu J of u du. And the new J's up in the formula for the discounted numeraire. The discounted numeraire d of t n of t is equal to, where's the formula? This formula, equal to d of t n of t, and let me write this out as a sum so we see it. J equals 1 to d nu J of u t dw tilde J of t. And so when we started out, we had more than one Brownian motion driving the numeraire. The new J's are sort of the factor loadings of the different Brownian motions, and those factor loadings, or I'll call it volatility vector, go into the calculation of the new Brownian motions. So we learned that, and we also learned that if you look at the quotient and ask what is the volatility vector for the quotient, it's the difference between the volatility vector of the numerator and the volatility vector of the denominator.
Should there be a negative sign there in the W and JT?
Let's see, so a negative sign here?
W and JT is equal to Wj tilde t minus integral 0 to t.
Yes, it should be. Thank you. Yeah, we subtract those out. When people think volatility in finance, they don't think about vectors, they think about scalars. And in fact, the volatility scalar, if you want to think what is the volatility of S and what is the volatility of the numeraire N, it's actually the Euclidean norm of these vectors. So when people in finance think about volatility, I'm thinking about a vector here of sigmas and a vector of nus. You should take the Euclidean norm, and then you would get what is commonly called the volatility in finance. I can give you an exercise to work that out. I don't want to stop right now and do the calculation. Okay, let me see how we're doing in terms of questions. Maybe I'll do that exercise right now and then we'll take a break. So let's just the stock price that we started with back here, or whatever asset this is. So we started with this formula. ds of t is r of t, s of t, dt, plus s of t times the sum. J goes from 1 to d, sigma j of t, dw tilde j of t. So I have D independent Brownian motions driving this, and I have a sigma j multiplying Brownian motion j. And what you can do is write this as R of t, S of t, dt, plus, I'll put here the Euclidean norm of S of t, and then here I have to divide by the Euclidean norm. Sum, j goes from 1 to d, sigma j of t, dw j of t. And then I'm going to define a Brownian motion. Well, we'll check that it's a Brownian motion as the sum, as the integral from 0 to t of the sum, j goes from 1 to d, 1 over the Euclidean norm, sigma j of u, dw j of u, and I'm forgetting my tildes here. I said that's a Brownian motion. Let's see. It starts at 0 at time 0, right? If you put t equals 0 into this, you'll get a 0 on the right-hand side. It's a martingale because it's actually a sum of Ito integrals. And so a sum of martingales, right? Each Ito integral is a martingale, and the sum of martingales is martingales. It has continuous paths, right? Because Ito integrals have continuous paths. And how fast does it accumulate quadratic variation? dB of t is, well, if I take the differential of this and then multiply it by itself, this Euclidean norm term will get squared. And then you'll get j goes from 1 to d, sigma j of t, dwj tilde of t, times the same thing. J goes from 1 to t, sigma j of t, dwj tilde of t. But when you multiply these two sums together, our Brownian motions that we're putting in here are independent. And so when you multiply them together, the only survivors will be where the same Brownian motion multiplies itself in both terms. So you don't get any cross terms. And so what this will give you is going to be the sum. When they multiply themselves, you'll get sigma j squared of t dt. This term cancels this term, and so you get just dt. And so I can pop back up here and write ds of t. So Levy's theorem says that B is a Brownian motion, and then I can pop back up here and say S of t is R of t, S of t, dt, plus norm of sigma of t, S of t, dB of t. It's common in financial circles when you write an asset price to write it not in terms of multiple Brownian motions as I've done there, but in terms of a single Brownian motion as I've done here. And then once you've done that, you read this term out and call it the volatility. So I'm doing it in a somewhat more convoluted fashion because I'm putting in multiple Brownian motions and putting factor weightings on them. But if you take the Euclidean norm of this vector of weightings, then you've got the volatility in the classical, traditional sense. There are many reasons why I want to do it this way, and you'll see those as we go forward. Let me pause here and see. Yes. So what was the takeaway? So before the break, the takeaway. What is it you're supposed to remember from this whole discussion? So a quotient of martingales is not a martingale unless you change the measure. Okay, I should qualify that a little bit. So I said at this point when we were doing this calculation and got the quotient of martingales, I said you can see here that you don't get a martingale because you get a dt term. If the numeraire had 0 volatility, then this nu would not be present. So a quotient of martingales could be a martingale if the denominator is constant, right? So except in that case, the quotient of martingales is not a martingale unless you change the measure. And to change the measure, use the denominator discounted if necessary to get a martingale. And normalized divided by its initial condition. So it starts at 1. As the Radon-Nikodym derivative. And then we had these two formulas. The one of them is the volatility vector subtract. So the volatility vector, the quotient, is the difference. Between the volatility vector of the numerator and the volatility vector of the denominator. As scalar does not mean they subtract, right? Because if you think of volatility in the traditional scalar sense, the volatility vector of the quotient is the Euclidean norm of the difference between the two volatility vectors, and the Euclidean norm of the difference is not necessarily the difference of the Euclidean norms. So as scalars, they don't necessarily subtract, but as vectors, they subtract. And the Brownian motion, I guess the only way I know to write it is the way it's written here. Here. So the Brownian motion, here I guess, the Brownian motions that you get under the new measure are the Brownian motions that you had under the old measure minus the integrals of the components of the volatility vector of the numeraire. Right, it's this equation here. How do the Brownian motions change? You take the vector of volatilities for the numeraire and you subtract off their integrals with respect to time from the original Brownian motions to get the new Brownian motions. So that's the summary of what we learned when we took apart the lock with our bare hands to see how we do this business of changing the measure to make a quotient of martingales be a martingale. So what I plan to do in the third hour of the evening is to go back to the problem that we began with. You may recall we began with pricing a caplet in the Ho-Lee model. And I said there's some function that one could solve, that we could write that caplet in terms of the time and the underlying interest rate. And I would like to actually compute that function, but it's a lot easier to compute that function if we change the measure first using these ideas. So what I'd like to do is take a 10-minute break and then come back and do that calculation to show you how this idea of change of measure can simplify lots of things. Is there any parting question before we go? All right, let's take another 10 minutes. Okay, why don't we wind things up? So we have our takeaway here. And then I would like to take us back. And let's think about doing this change of measure. And we're going to get something called the forward measure. And I'm going to do it in the Ho-Lee model. So let me remind you, dr is very simple. A dt plus sigma dw tilde. We're starting with a Brownian motion under p tilde. I don't expect to have all these formulas in your head. If you need one of these formulas, either the problem will be to derive it on the midterm exam, or if I don't want you to derive it, I won't ask you to remember it, I'll just give it to you. Here's the formula for the bond price in the Ho-Lee model. So it's minus t minus cap t minus little t, r of t, minus 1/2 a cap t minus little t squared, plus 1/6 sigma squared cap t minus little t cubed. And so we worked that bond price formula out, and then I believe, I can't remember what's been done in lecture and what's been done in recitation. In one of those places we computed the differential. It's not hard, right? I think I did it in lecture. No, I think Ted did it in recitation. You have to, because I remember this discussion. So when you compute the differential of the bond price, for some reason, students forget to use Ito's formula here. I don't know why it happens here, but here it happens. What you have is a random process. Here it is. It's random because the R of t is random, and it's sitting in the exponential function. So you have to use the exponential function, and you're going to get f prime of the differential of this plus 1/2 f double prime of the differential of this. You have to use Ito's formula when you work out the differential of the bond price. If you do that, and you may want to practice this at home, you get this formula. This is a dt. This is not surprising. Mean rate of return is equal to the interest rate, right? Bonds are an asset. Mean rate of return equal to the interest rate. We have only a one-dimensional Brownian motion here, so our volatility vector is actually one-dimensional. And here it is, and it has a minus sign associated with it. So this is the volatility. It doesn't bother me to put minus signs in front of volatilities. I think of this as a one-dimensional volatility vector. And if you want to talk about volatility in the traditional sense, you need its Euclidean norm. And of course, in one dimension, the Euclidean norm is just the absolute value. But I carry the minus signs along because they are important, because we have these formulas about subtracting and adding, and we need to keep track of the minus signs. So there's the volatility. That you would not know that that's the volatility unless you actually did the calculations, which we have done. I'm just recalling them here. The one thing that you do know about volatility for these zero coupon bonds is that as you get close to maturity, the bond price is going to 1, and in order to do that, the volatility has to turn off. And you see that right here, that as little t goes up to capital T, the volatility goes to 0 because the bond price is converging to a constant. We also have this process S of t that we've been talking about. So here's the risk-neutral pricing formula. S of t is the price at time little t of a contract that pays R of capital T at time capital T. and I'm computing S of little t by the risk-neutral pricing formula, and somewhere along the way we worked out this formula. Actually, I did this in class. It's the bond price, and then it's R of little t plus A of cap t minus little t minus 1/2 sigma squared cap t minus little t squared. And in your homework that you turned in, you've turned in one homework, right? The homework that you're about to turn in, you're going to work out the following equation. You're going to work out the differential for S of t. So I'm giving away an answer here. Okay, so when you compute its differential, you should get that. So this is the volatility of B, and this is the volatility of S. Notice again, mean rate of return is equal to the interest rate. Let's think about forward prices. So the price of S, the price at time t for delivery at capital T of 1 unit of S. So this would be the forward interest rate. Right? It's the forward price for the interest rate at capital T. Will turn out to be the forward interest rate, the interest rate you can lock in now for borrowing at capital T. So we worked out this formula last week that forward prices were the price of the underlying asset divided by the bond that matures at the date of delivery. So that was from last week, and I can write this as a quotient of martingales. So that was a martingale, at least not under the risk-neutral measure, but we can make it be a martingale, and that was the whole discussion of the takeaway. Quotient of martingales is not a martingale unless you change the measure. To change the measure, use the denominator. Discount it if necessary, and normalize so it starts at 1. So we're going to change the measure, and I'll define a new measure. I'll call it P capital T, and I'll use the denominator at the final time capital T, normalized if necessary so that it starts. And remember that B of capital T is just 1. That's the maturity of a zero coupon bond that pays 1 at maturity. So there's the way we would change the measure in order to make the forward price be a martingale. The volatility vector of the quotient is the difference between the volatility vector of the numerator and the volatility vector of the denominator. So what is the volatility of the forward price? It's the difference between the volatility of the numerator, which is S, and the volatility of the denominator, which is B. So here's the volatility of the numerator. Sigma B of cap T over cap T divided by S of cap T, S of little t minus cap T minus little t. So that's the volatility of the numerator minus the volatility of the denominator. So here's the volatility of the denominator. it already has a minus sign, and then I take minus the volatility of the denominator, so I get plus sigma of B of little t cap t, I'm sorry, sigma of cap t minus little t. And you see that the sigma times cap t minus little t cancels, and so I get sigma B of cap t, little t cap t over S of little t. And that's actually the reciprocal of this. So it's sigma over the forward price. And what was part of the formula? The takeaway is how we find our new Brownian motions. So here we have only one Brownian motion, so I don't have to do this. Here we had D, but in the case we're working with, D is 1. And so I'll call this the forward Brownian motion, W capital T of little t is W tilde of little t minus the integral from 0 to little t of the volatility of the denominator. The volatility of the denominator is this minus sigma thing. So minus sigma of t minus u du. So this is actually W tilde of t plus sigma of the integral from 0 to little t of t minus u du. And if you do the integral there, you'll get W tilde of t plus 1/2 sigma t. That's not right. My notes only have it written down. Ah, yes, here it is in my notes. If, I'll have to do it. Okay, so what is it? W tilde of t. I'm integrating with respect to u, so I'll get a minus 1/2 sigma t minus u squared. Integrated, u goes from 0 to equals little t. W tilde of little t minus 1/2 sigma cap t minus little t plus 1/2 sigma cap t squared. If I write it in terms of dw tilde, dw tilde of dw forward of little t is dw tilde of little t, and then just take the differential here with respect to the t. The two minuses give you a plus, and you get plus sigma cap t minus little t dt. Right? If I integrate this equation, I get that equation, which still doesn't seem quite right to me, but so be it. Okay. Okay, so I've done this. I'm doing the switch. There should be a square here, right? That looks better to me. So somewhere you derive the forward. I think I'll give away more of your homework problem. Oh, I think we did this already. What is the forward price? Okay, it's the S of t over the bond price. And we worked that formula out in class. There's S of t right here. If you divide it by the bond price, then you get R of t plus A of cap t minus little t minus 1/2 sigma squared cap t minus little t squared. Okay, that's not a martingale under the risk-neutral measure. That's a quotient of martingales. Right? It's this quotient of martingales, so it's not a martingale. Let's take its differential and we'll see that. So it's dr of t minus a dt. And then when I take the derivative over here, this minus will get killed because I have a minus little t. The 2 gets killed, the half gets killed by the 2. And so I get plus sigma squared t minus t. dr of t is a dt plus sigma dw tilde of t. And then we have a minus a dt. And then we have a sigma squared cap t minus little t. And so I get a sigma dw tilde of t plus sigma cap t minus little t. That's a dt term. And we recognize this. It's not a, right, we don't have a martingale under p tilde because of the dt term, but the forward Brownian motion is exactly the thing that's sitting in the square brackets. And so once we change the measure to the forward measure and make w capital T be a Brownian motion, then in fact here we have sigma dw tilde capital T of little t. And what is the volatility of the forward price? Well, if I want to think about volatility, I need to have forward price dw tilde capital T of t, and then the volatility goes right here, and so that would have to be sigma over the forward price. And this then is the volatility of the forward price. Which is what we predicted back here that we would get, right? It's the difference between the volatility of the numerator and the volatility of the denominator. So what I'm arguing here that everything makes sense, right? That this change of numeraire that we were talking about when applied to the Ho-Lee model, and in particular when applied to the forward price, which is really a quotient of martingales, is going to give us all the results that we expected to get. The change of measure works the way we thought. The volatility subtract the way we thought. The Brownian motion under the new measure works the way we thought. And the forward price, the quotient of the martingales, becomes a martingale when we switch to the Brownian motion under the forward measure. This is actually a common trick when pricing fixed income derivatives, is to switch to the forward measure, and you choose the forward measure, right? For each capital T, you have a forward measure. You choose the forward measure that at time capital T that corresponds to the payment date of whatever the derivative security is. And this is the Radon-Nikodym derivative that we see to do that change. And the reason that works so well, the reason we do that is because it works really well when doing pricing, and that's the next thing I want to show you. So I'm going to show you why we're interested in doing this in the first place, but let me check and see if you're comfortable with my calculations. I did several of them here quickly, but what I'm doing here is just in the Ho-Lee model, I'm just applying all the items that are written down here on this takeaway page. Okay, so not hearing any objection, I will push forward. We want to keep this page where we can see it. Except now that I've lost my count. I guess we're on page 18. So let's look at the caplet price. I'm going to price it at time 0. We could price it at other times as well, but let me do just time 0 so as not to make this any more confusing than it has to be. So I'll discount from the final time back to time 0, and then the caplet payoff is the instantaneous interest rate at capital T minus K positive part. And the reason the fixed income derivatives are hard is because of the correlation, right? The discount depends on the interest rate, and the payoff depends on the interest rate, and you have to worry about the correlation between these two. And not only that, if you write down what d of capital T is, it involves e to the integral, or e to the minus integral of the interest rate. So that's kind of a mess to try to think about computing the distribution for. So here's the trick. Let me multiply by the price at time 0 of the bond that matures at time capital T. And of course, if I multiply by that, I have to also divide by it. And it's not random, so I can multiply outside the expected value and divide inside the expected value. And this term right here is the Radon-Nikodym derivative that switches us to the forward measure. And so I write this again. But now I'm taking expected value not under the risk neutral measure, but under the forward measure. So the correlation problem is gone. Okay? Now we have to figure out what is the distribution of R of capital T under the forward measure. So let's remember how that goes. R of capital T is R of 0 plus A capital T plus sigma W tilde of capital T, right? You know where that's coming from. I'm just integrating the formula somewhere. We have R, who knows, there it is. There's R. Integrate this from 0 to capital T. And when you do that, you'll get R of capital T minus R of 0 is equal to A times capital T and sigma times W tilde of capital T. So that's just integrating the Ho-Lee model. And now somewhere we have a formula that tells us about the relationship between W tilde of the forward Brownian motion and the risk neutral Brownian motion. And we're putting in a capital T here. And so let's just do it here on the side. That formula says that W, the forward Brownian motion at capital T, is equal to the risk neutral Brownian motion at capital T. I'm evaluating that little t equals capital T, so this term goes away. And I have plus 1/2 sigma capital T squared, right? So that's coming from page 16. So here I put in R0 plus A capital T plus sigma. And so W capital T, the risk neutral Brownian motion, is the forward Brownian motion minus this term. So this is T of T minus 1/2 sigma capital T squared. So I'm going to write that as R of 0 plus A capital T minus 1/2 sigma squared T squared plus sigma, actually let me do it this way, minus sigma square root of T, capital T times Y, and the Y that shows up here is minus the forward Brownian motion at capital T over square root of capital T. What I'm doing is I want to write things in terms of a standard normal random variable, and W capital T at capital T is not standard normal, it has variance capital T, so I'm dividing it by its standard deviation to get a standard normal. And why do I put a minus sign here? Well, it's because it makes the formula look a little more like Black-Scholes than if I'd left a plus sign. So W capital T over of capital T is sitting right here. This minus is canceled by this minus in the Y. This root capital T is canceled by this root capital T. And so if you work this term out, you see that what you get is sigma W forward of capital T. This is standard normal under the forward measure. We're pricing a caplet, so we're interested in when does this expire in the money. That is, when is R of capital T bigger than or equal to K? Well, that would be r of 0 plus a capital T minus 1/2 sigma squared capital T minus sigma capital T times the standard normal random variable y bigger than or equal to k. Let me rearrange this. I'll put the y on the other side. So on the left-hand side, I'll have r of 0. I'm going to bring the k across.
Professor,
Question?
the half sigma squared t squared.
I'm sorry, is there...
There should be a sigma squared t squared in the first term.
The t squared here, yes. Yeah, thank you. I'll bring the k to left plus a capital T, a times capital T, minus 1/2 sigma squared capital T squared. The y is going across, and then I'll divide by sigma over root capital T. Okay, do you agree with this? Let me call this D. I'm going to try to make this look like a Black-Scholes formula. Right, so we're in the money if y is less than or equal to D. Right? And r of capital T is sigma square root of capital T D minus y plus k. I don't know, can you see that right away? If you take, actually I'm not sure I see that right away. Yeah, I guess so. If you take this, that's D, you subtract y from it. No, this doesn't even look right to me. The k seems to be in the wrong place. D minus y. I don't believe D is in the right place. I think it should be like this, right? I'll just give you a moment. I'll shut up and give you a moment to look at it. This is R of capital T right here, right? If I take this, pull the y across, then multiply by sigma square root of t, I'll get all of this, but I'll also have a minus k that I don't want, so I add it back on, and then I get this r of capital T. And now let's do the pricing. So we're trying to compute this term. That's right. The caplet price is the bond price times this term. Let me do the expected value. So that's the expected value under the forward measure. R of cap T minus K. According to this formula, R of cap T minus K is this stuff. So that's sigma root T D minus Y. But you only get this if you're in the money, if R of cap T is bigger than or equal to K. And R of cap T is bigger than or equal to K if and only if Y is less than or equal to D. So I'm going to put here an indicator. Y is less than or equal to D. So the sigma over square root of T can factor out. under the forward measure, y is standard normal, right? Y is standard normal under the forward measure. So I'm going to integrate with respect to the standard normal density from minus infinity up to d, right? Because we only get this term if we're in the money, y less than or equal to d. And what do I integrate? D minus y, e to the minus y squared over 2 dy. First is sigma square root of t times d times 1 over square root of 2 pi integral minus infinity to infinity e to the minus y squared over 2 dy. That's the d term. And the other term is minus sigma square root of t 1 over 2 root 2 pi minus infinity to infinity y e minus y squared over 2 dy.
Shouldn't the upper limit be d?
It should be d in both cases. Thanks for keeping me honest. So this is just the normal cumulative normal distribution at d, right? So the first term is sigma square root of t d n of d. The second term I can actually integrate. And so we're going to get a minus sigma square root of t. And then I guess we'll get an e to the minus y squared over 2. And this will be a plus sign when I integrate it. Evaluated at y equals minus infinity and at y equals d. Oh, and I forgot my root 2 pi. This over root t factors out. D times n of d plus 1 over root 2 pi. When I plug in the upper limit of integration, I get minus d squared over 2. When I plug in the lower limit of integration of minus infinity, I get 0. And this is the normal density evaluated at d. So what I have in the end is sigma square root of t d n of d plus n prime of d. So price at time 0 is b of 0t, and I'm just recalling this formula, b of 0t, and then we've computed that, sigma square root of t d n of d plus n prime of d. And let me remind you of what d is. D is 1 over sigma root t r of 0 minus k plus at minus 1/2 sigma squared t squared. Okay. This is a pretty neat trick that gets used frequently. Again, the trick was here you had correlation. And we removed it by multiplying and dividing by the bond price and then seeing this as the term that would change us to the forward measure. And now we just have to compute under the forward measure, but we don't have to think about correlation anymore. I will point out to you that we've only priced the forward contract at 0.0. We could certainly price it now at other times, and if you look at the formula we have, you can guess what the formula is going to be at other times. So suppose we were sitting at time little t. I may have said the wrong thing. So this is the caplet price. We're pricing a caplet. Suppose we're sitting at some time other than 0, and the interest rate at that time is r rather than R of 0. Then what you would put here is the bond price at that moment. And the bond price is somewhere there it is. That you put in the bond price. And so that's exponential minus t times the interest rate at time little t minus 1/2 a t minus t squared plus 1/6 sigma squared t minus t cubed. That's the bond price. And then you put in sigma and then the time till expiration. And then you have this term, d n of d plus n prime of d. And the d is given by this form dated to time little t. So 1 over sigma, and then instead of capital T, you have the time till expiration. Instead of R0, you have R minus K plus A, time till expiration, minus 1/2 sigma squared cap T minus little t squared. We started at the beginning of the hour, and I said if we're going to price this caplet, we know from the Markov property that we're going to get a function of time and interest rate, and here's the function. And we said that it satisfies the partial differential equation on page 1. That'll be your homework problem, to check that indeed this satisfies the partial differential equation on page 1. It's clear that it satisfies the terminal condition. The terminal condition is that when little t is capital T, you get R minus K, positive part. If little t is capital T, this whole term is a 1 because all of these expressions are 0. This looks like a 0 sitting here, but in the d that sits here, there's a 1 over capital T minus little t. And so this d term has this leading term, and it cancels that term. And then you're going to get the R minus K showing up in the d term. But about the n of d, well, it'll either be plus 1 or it'll be 0, depending on whether you're in the money or out of the money. And so it's going to produce for you this terminal condition, this, let me put it where you can see it, this R minus K positive part. So I described that for you in the homework problem. You can work through that and see that we have, in fact, produced a solution to the partial differential equation that satisfies the terminal condition. In the very few minutes that I have left, let me tell you about Black's formula, because we've almost done all the hard work. So Black wrote this formula down many years ago before anybody knew anything about forward measures or even risk-neutral pricing very well. And he was working in the fixed income department at Goldman Sachs, and he had to think about options on interest rate derivatives. And he thought, well, there ought to be some kind of variation on the Black-Scholes formula, and indeed there is. So the story is the following. So we have S of t, so it's some asset price. We have B of little t capital T, which is the bond price. And then we have the forward price for S. S of t over the bond price. Let's assume that the forward price has constant volatility. So the differential of the forward price is a constant. times the forward price, dW forward Brownian motion of T. Right, it's a martingale under the forward measure, and so I'm using the forward Brownian motion here. But let's assume furthermore that the volatility is constant. You don't need to do that in order to do our calculations. We just did a calculation in which the volatility of the forward price was not constant. But under Black's formula, we make that assumption, and then we price a call on S. So the price at time 0 of a call on S is, well, here's the risk neutral pricing formula. And in Fisher-Black's world at Goldman Sachs, the S was something that depended on the interest rate, and so correlation here was a big issue. And so we do exactly the trick that we just did. D of capital T over bond price. And let me make one other change. At the final time, the forward price is the price of the asset. So in place of S of capital T, I'm putting in the forward price. They're the same at the final time. This changes the measure. So I have B of 0 capital T, E under the forward measure now of the forward price but assume that the forward price has constant volatility, right? This is the differential of the forward price. Then we know what the forward price is at the final time. This tells us that the forward price at the final time is the forward price at the initial time times exponential sigma forward Brownian motion at the final time minus 1/2 sigma squared times time. This different stochastic differential equation has a solution that we can write down. There it is. Right? It's the geometric Brownian motion exponential martingale thing. It's like a geometric Brownian motion, except there's no interest rate here because there's no drift in the forward price. And so what we get is B of 0 capital T, E forward, and then we get forward price at the time 0 exponential sigma W capital T of capital T minus 1/2 sigma squared capital T minus the strike positive part and we know how to compute that. That's a special case of a Black-Scholes calculation. In fact, the formula would be the following. We'll have this bond price sitting out front. And then Black-Scholes says you will get, this will be like the initial stock price, so you'll get the forward price here, N of D plus, minus K. There is no interest rate here, right? There's no discounting in front, there's no R in here, so it's like an interest rate 0 Black-Scholes formula. And so I don't get an E to the minus RT here, but I get an N of D minus. And the D plus and D minus are the usual things. 1 over sigma times the square root of time till expiration log of the forward price over the strike price plus or minus 1/2 sigma squared T, right? There's no R. R is a 0. Voila, right? This is Black's formula. So price of a call on any asset when the interest rate is random under the assumption that the forward price has constant vol. And in fact, it's now used as a quoting convention. In the same way that Black-Scholes is not quite right, but it's used as a quoting convention, Black's formula even if the vol is not constant, is still used as a quoting convention for prices of options on interest rate contingent assets. All right, are there any questions? If you stare at this formula long enough, you realize that there's a replication being suggested. We'll probably talk about that some more if time permits. If you think about this formula for just a moment, so Black's formula. If you multiply the two together, you'll get S of 0, right? The forward price is S of 0 over B of 0. So these two together will give you S of 0, N of D plus, minus, move this over here and you get K, B of 0 T, N of D minus. If you want to replicate the call, one way to do it, you can sort of see here, is if you go long N of D plus of S and short K N of D minus bonds, then you would have a portfolio whose value was the same as the value of this call. And that's, in fact, a replicating strategy. That will finance itself. So as time moves forward, the D plus and the D minus will move, right? Because this capital T will be replaced by time till expiration, and the forward price will start to move here. And so the D plus and the D minus will move, and it will tell you how to update your portfolio, and in fact, that replication will work. You have to do some calculations to see that it finances itself, but it does. Okay, so now I'm really done, and I will see you in New York next week. Let me see, any parting question before we go?
Will you give us review exams for the midterm?
I put up, so the last time I taught this.
Oh, nice.
The last time I taught this course was in 2007. Casper Larson has been teaching it since then. And so I went back and found in 2007 I gave a midterm exam, and I put that up this afternoon with some caveats because I'm not doing exactly the same thing 6 years later that I did in 2007. And so I've made some comments about what you should not take so seriously on the exam. But I did put up the last midterm exam that I gave. I will wait until Monday to put up the solutions. The reason for that is I think it's really easy to take an exam and sit with the solutions in front of you and say, oh yeah, I could do that. Oh yeah, I could do that. Oh yeah, I could do that. And it's a little like being led through a minefield, and you don't even notice that the mines are there until your guide leaves you alone, and then you get an arm blowing off or something. And so you really need to try an exam without having the solutions in front of you first. So it's there, and you can do it this weekend, and then on Monday the solutions will go up.
Oh, will there be a review session?
Yes, so I'll have a review session. I'll do a review session with the Pittsburgh students on Monday, and that's going to actually be sent to New York, so you can tune in Monday afternoon if you're present. It'll also be recorded, so you can tune in Monday evening if you're not present. And then I'll do a review session in New York in the first half of the Tuesday evening session. We'll do a review session and then take a break and give the final exam. And I'll also be there for office hours with you guys Tuesday afternoon.
Thank you.
Okay, see you next week.